So let me start by introducing today's speaker, which is Stuart Holmes. Stuart Holmes, he got his PhD from Imperial College, and then he was a NATO postdoctoral fellow in New York. And after that, he worked for the Toshiba Research Center in Cambridge for about 20 years, and he worked on quantum information-based projects, often in collaboration with the Thin Film and Magnetism Group at the Cavendish Laboratory. And now Stuart Holmes is on a senior research position at the London Centre for Nanotechnology, and he's a visiting professor of electrical engineering at UCL. And today he's going to tell us about photon-assisted processes, suppression of photon-assisted processes in InGaAs structures. So with that, Stuart, thank you very much for agreeing to come and give this talk. We're very much looking forward to it.
Thank you, David. Thank you for the invitation and thank you for the nice introduction there. So I just want to spend half an hour or so explaining what we've been doing, what the types of measurements that we've been doing, some of the goals. The work is fully funded by the EPSRC. It's a program grant. It consists of several partners. The main partner is UCL, Professor Pepper in UCL. We have Dave Ritchie and Professor Charles Smith in the Cavendish Laboratory. We also have partners in Royal Holloway, University of London, James Nichols, ex-Cambridge, and Aditya. We also have theoreticians in Birmingham that we interact with. Sorry, I've got a very small screen here. I'm just moving things around. We've got theoreticians in the University of Birmingham in physics there. We've got Igor Lerner and Ian Van Beek, and several students that work on this. So what I want to tell you about today is our progress towards making freestanding, thermally isolated, but well-behaved 2D electron systems or Hall systems. The work that I describe is mainly done with Chong Chen and Abby Low at the Cavendish Laboratory, with some help from Georgios and also from Yilmaz Gul in UCL. So why do we want to try and suppress phonons? Well, it's to really uncover some of the details of the metal-insulator transition, what happens at low temperatures or high disorder or low doping densities. So the summary here is what I'll discuss, some details of the metal-insulator transition, some details about how transport occurs in that transition region, be it hopping or diffusion. I'll tell you about how we make these three-dimensional, two-dimensional semiconductor devices that actually behave as one dimension. So we've got all the dimensions there. A little bit about thermal isolation, and some of the conductivity measurements that we do, conductivity with disorder, and some of the implications for this study for many body localization when we've got interaction. So some of the experimental problems in the build up to this work, I mean, Anderson localization has been with us for 50 years or so, possibly more. And some of the experimental problems that have persisted during that period has been that when you have a variable range hopping mechanism, the high temperature the high temperature pre-exponential on the conductivity or the resistivity was quantized to in resistivity h over e squared, or in conductance e squared over h. So that was always a strange phenomenon, that you've got a thermally assisted process, yet the pre-exponential was the simple quantum of conductance. The other problems which we've seen was when you have a Fermi level that's in a localized state, you have an activated conductivity. But if you measure the Hall effect, you get all the carriers. The carriers are not activated, which seems very, very strange. Also, the types of physics that we use to describe what's going on is very, very similar on both sides of the metal insulator transition. And also, intriguingly enough, if we are in a region of activated conductivity, the mobility, which is also thermally activated, that activation energy seemed to depend on where the Fermi energy was in the band. So the mobility edge was moving in the band as a function of carrier density. Very strange. So the question was, do these anomalies arise from perhaps a more fundamental mechanism which is going on in the system, perhaps an incipient many body localization? So I've just grabbed a quick introduction here. If you go to Boris Altshuler's website or or Wikipedia, you are inundated with a plethora of lecture notes on this, hundreds of view graphs on this. Very, very interesting if you've got time to look at those. A many body localized state is a true random glass state. It's non-ergodic. That's one of the properties of the system. So a small part of the system really doesn't represent the global system, even when you've got interactions going on in the system. And also, when we learn physics at school, we learn thermodynamics and about equilibrium, and the fact that actually what we don't learn is that when you have a many body localized system, the system doesn't come to a thermal equilibrium, even with interactions. So thermal effects are very, very important in this system. And at low temperatures, the system is a perfect insulator. Electrical conductivity goes to zero, thermal conductivity goes to zero at finite temperature, not zero, but finite temperature. And the system itself could actually be used for quantum computing or quantum information, where we can preserve an initial state. It's very good, it's got long-term memory, we can preserve the initial state, it doesn't interact, and so on. Very useful for that. So going back to some of the transport measurements, I'll just explain the different regions of transport measurement, different behavior of transport mechanisms that we might observe. This is an experimental setup here. This is a resistor from the lab. If we were to measure the properties of this resistor, we'd pass a current through it, we'd measure a voltage, or we'd apply a voltage and measure a current. The device conductance is a very simple relationship. Device conductance is the current divided by the voltage, or the resistance is the voltage divided by the current, whichever angle we're looking at the problem from, conductance or resistance. And conductivity and resistivity are normalized by the size of the device. So what happens in a doped semiconductor at high temperatures, at say an extrinsic semiconductor at high temperatures? We describe the system as diffusive. Diffusion in semiconductors is one of the basics that we learn as an undergraduate. We learn about p-n junctions. To understand a p-n junction, we look at how the charge diffuses and drifts across the interface. It's very, very important to understanding transport in semiconductors. You can describe the conductivity as n(e²) tau over m star. Any temperature dependence comes from a temperature dependence of n, or tau, which is the scattering time, momentum scattering time. As we cool down the sample, go to lower temperatures or to lower carrier densities, what we find is that some of these quantities become activated, thermally activated, so we pass through a thermally activated region. It could be an intrinsic semiconductor, where we've got carrier activation, thermal activation across a band gap. It could be carrier freeze out through doping. We pass through an activated region into the metal-insulator transition, And in the metal-insulator transition region, we describe the system with a mechanism called hopping. So the charge hops between vacant states in the lattice. And interestingly enough, we describe that by an exponential. So the resistivity at some temperature T is a prefactor ρ0, which is the high temperature limit. and then an exponential with some characteristic T0. T is the variable temperature, and P is a power. Now, if we were in the activated regime, this power P would be just 1, and T0 or K, T0 would be equivalent to an activation energy. But what we see in this hopping regime is that we have the system behaves in this way. If the power P is a third, we're in the so-called Mott hopping regime. And the prefactor, which is quantized, is a half of h over e squared. At lower temperatures, we shift over to a different type of variable range hopping called Efros-Shklovskii range hopping. The power changes, P is a half, and the prefactor rho 0 changes. Interestingly enough, in terms of diffusion, when you're in the Drude region, we got a diffusion constant that's something like an electron frequency, and when we're in the hopping regime, we've got something like a phonon frequency, and they can be 3 orders of magnitude different. So previous data on this, I've picked 2 specific examples here, is Seifel Kondaker's work that was done actually fairly recently, 1999, at the Cavendish Laboratory, and Arindam Ghosh. Now, this transition between the 2 regions of variable range hopping can be typically a carrier density of about 10 to the 11. It's a reasonable doping in a 2-dimensional system, and about 1 Kelvin. That would be the typical experimental regions. The Efros-Shklovskii mechanism is very interesting. When we get into this region at low temperatures and low carrier densities, the transport of charge through the system is by hopping. This is a schematic. This is a state here. The electron or hole hops into a vacant state. It's phonon-assisted. There could be so this is called variable range hopping. So this distance here between a vacant state and an occupied state can be quite long in the crystal at low temperatures. There's also a mechanism called just hopping, where the electron could hop between localized states from a donor. It could hop between donors in the system. When we have this Efros-Shklovskii mechanism, the energy that's involved in the transition is not simply just a difference in energies between the 2 states. There's also an excitonic term. So when the electron hops, it leaves an image charge, a positive image charge. The positive image charge and the electron form an excitonic state. And there's a correction. There's a kind of a bound state correction to this energy here, delta E. And the correction is the Coulomb interaction between the whole image and the electron charge. Now, if this was an actual exciton, this distance here would be something like the Bohr radius. But in the hopping regime, it's actually the hopping distance. So it can be quite a small energy correction. And that changes the hopping conductivity. This energy correction here changes the hopping conduction. The power here becomes a half. And that's published 1975, Efros-Shklovskii. Looking at some of the early experimental data on this, this is a delta-dope. This is a 2D gallium arsenide system. It's delta-doped. The delta-doping adds disorder. The delta-doping is very close to where the charge is confined in the 2D region. As the resistivity is measured as a function of temperature, actually this is 1 over T to the 3rd. So this is in the so-called Mott regime. At fairly higher carrier densities, it behaves as if it's variable range hopping through the Mott mechanism, so non-interacting charges. And then at lower carrier densities, this is changing the carrier density with a gate. The system doesn't behave as if it's a Mott. It switches over to Efros-Shklovskii. So if we replot the same data, 1 over T to the half, then at the lower temperatures, we have this activated behavior according to Efros-Shklovskii. So at lower temperatures, this larger hopping distance comes in with the extra term. You can see clearly the high temperature intercepts h over e squared for Efros-Shklovskii, h over 2e squared for Mott. Very interesting. And just a little bit more detail on that. If we're in this Efros-Shklovskii regime, if we normalize the temperature to the characteristic temperature for each carrier density and then plot them out, they have a kind of a universal behavior. They all fall on the same line. Intercept is just h over e squared. Very interesting. Why should that be? It's thermally assisted. The phonon should introduce a factor of about 10 to the 4 in the prefactor, but the prefactor turns out to be just h over e squared. Very interesting. Some more detail on this. There's a little bit more experimental background, a little bit more detail here. This work can be carried on in high mobility materials, not necessarily induced disorder, but kind of in an intrinsic disorder in the system due to just regular doping. So a high mobility device, which has low disorder, but if you go to low enough carrier densities, this is a few times 10 to the 10, the prefactor is still quantized. So although you haven't introduced disorder, the prefactor is still quantized. So this is the Efros-Shklovskii mechanism here in this much more lower disordered system. And when the data was looked at in a little bit more detail, it was found that the prefactor, although it was quantized, it actually changed in steps of a half h over e squared. So when you looked at this in more detail, it was even more interesting that they structure this to this prefactor. Another way of looking at these systems is to consider them as a kind of the wave nature of the system. So we have this expression here for the resistivity, which is RC is a critical range hopping between sites, and this variable here is the interaction length of the wave. So you consider it as a wave packet. It has some kind of localization length associated with the wave packet. So you can also explain the data with this equation. What happens at very, very low temperatures is that the hopping distance gets very, very large, gets comparable to the size of the device. So once your hopping distance gets comparable to the size of the device compared to the localization length, things become independent of temperature as the hop distance becomes longer than the device. So at lower temperatures, the device switches off. So coming on to what I've been doing and why I've started to look at InGaAs for these systems. What does InGaAs offer? It's got very similar device properties to gallium arsenide. It's easily grown. The Cavendish laboratory has great MBE chambers for growing this. We can process it. We can introduce disorder through doping, Deltadoping. But also we've got spin, and in the localization problem, spin is usually ignored. It's usually a factor of 2 somewhere, but it's usually ignored. So my interest was, let's put spin back into the problem. In InGaAs, spin is dominated, the spin scattering is dominated by a so-called Diakonov-Perel scattering mechanism, and the spin flip rate, this quantity here, is determined by the spin precession from the Rashba component in the Hamiltonian, and it's also proportional to tau m, which is the momentum relaxation time. So the momentum relaxation time can be very, very low due to disorder. So that means that the spin precession rate is very low, so the spin lifetime is very long. It also may enable us to study the prefactors. Do they depend on spin? Excuse me. InGaAs has got a very high spin orbit coupling strength. So the spin degeneracy is partially removed at 0 field. We don't need an external field. It's got a high G factor. If we were to apply a magnetic field, The spin energies are large through the Zeeman effect. It's also got a low effective mass, so applied magnetic fields, perpendicular fields, have a much larger effect on the localization properties. And also, perhaps the noise characteristics might be different in this system. So, moving on to how we make these devices, I mentioned that they are freestanding. So we start. This is a picture of the conduction band. This is the surface here. This is the InGaAs quantum well here. The little plus signs there are the doping that we put in, the Deltadoping that add disorder. So electrons in the quantum well here really feel this disorder. The rest of the structure is kind of buffer layers to the quantum well and a very, very thick InGaAs layer. Now this very, very thick InGaAs layer is then later removed by etching. If it's removed, the actual electronic system looks something like this. We've got a free surface here. We've got band bending due to charge. We've got the fixed charges, the fixed positive charges in the lattice that the electron gas sees. We've also got this new free surface here that we've etched away. That's this surface down here. So what does it look like when we've etched it away? It looks like this. This is 120 nanometers thick. They still conduct, just about. Interestingly enough is if we look at their magneto-transport properties, so this is putting a perpendicular magnetic field on. In the higher temperature regime, we can see a Shubnikov-de-Haas effect, change of carrier density. The mobility that we measure depends on the carrier density to the power 1. And that tells you straight away that the electrons in the quantum well really feel that disorder. They don't, it's not remote ionized impurity scattering, it's ionized impurity scattering from the doping that we put in at the interface. If we're in the high mobility limit, this is actually a slightly thicker layer. This is a gallium arsenide layer, just for comparison. This is a freestanding gallium arsenide layer here. This is all freestanding. Everything that you can see there is freestanding above the substrate. It's anchored, it's thermally anchored at the ohmic contacts, but here it's just freestanding. We see very, very clear quantum transport. This is not in the disordered regime now. This is just a comparison. We get a reduction in the mobility, but in the thicker layers, we only get a very small depletion of charge. We've created a new surface, and there are surface states associated with that. But in these slightly thicker layers, we just don't see that. We also are very lucky that the processing that we use, there's no edge. You can go into the edge state transport regime, so the kind of the quantum transport regime, and there's no edge state reflection in the system. You can properly measure the 2D parts of the system. And we did a quick study on this a few years ago, looking at the breakdown in non-dissipative behavior to really try and understand what these thermally isolated systems look like. We studied non-dissipative breakdown of the quantum Hall effect. It's kind of a stochastic behavior, but there's a very, very clear difference. This is an SEM image here. This is the 500 nanometer InGaAs layer, which is etched away. When you remove that, there's a clear difference between an isolated and a thermally contacted device. It was published in APL this year. This is what happens at slightly lower temperatures now. This is a disordered gallium arsenide device. This is at 12 millikelvin. This is cooling the device down to low temperatures. And what I've had to do is just illuminate the device, just to use a persistent photoconductivity effect to put carriers in there. These were the first devices that weren't gated, so we couldn't use the gate effect to go down to very low carrier densities. We had to rely on the fact that they're insulating in the dark and just use an in-situ LED device just to illuminate. We already see some very low field magnetoresistance, weak localization. We see this noise effect. You might say, well, Stuart's no good at doing measurements. They're full of noise, but it's actually reproducible noise. It's actually conductance fluctuations. I've plotted this as a function of filling factor, and as you change the carrier density, they all line up. So fairly well behaved at low temperatures. If we plot out conductance against carrier density, So this is at 12 millikelvin. I was trying to find the critical carrier density where the device went insulating. You can see this is conductance, it's dropping down. This is the point here. So we're still just about diffusive in this device at low temperatures. Going back to the InGaAs, what happens when we take the thicker layers, but grow new devices and make them thinner? We calculated that we could study a 2D system that's about 120 nanometers thick if it was no more than about 8 microns in size. And this is what happens here. This is a strange angle SEM image, courtesy of Georgios in the Cavendish. This is the Hall bar channel here, and these are potential arms that contact the channel for measuring voltages or currents, voltages, impedance. You can see where the sacrificial layer has been etched away and partial collapse. So we already know that this, even at 8 microns, we're kind of pushing how these devices will stand up. A few more SEM images. This is a kind of a failed device. The gate metal has just missed the top of the meso. These haven't collapsed. The latest devices, this is another SEM image. This is looking down on the device. These are completely freestanding. These are metal contacts that would be used for perhaps E-beam defined devices. This is all optical lithography. This is a kind of a large area gate over here. But this is all, you can see where the etch has gone through underneath here. This is completely freestanding. Very, very nice structures under the microscope. Slightly difficult to measure. This is what the gating characteristics look like. So I'm plotting resistivity now as a function of gate voltage. This is that same device under the SEM, from the SEM. You can see I've put red areas here. And I think what happens is these red areas deplete first. You can even see some breaks in the device here. So this is the gate characteristic. This is gate voltage. So if we start from 0 gate voltage, they are completely depleted. They don't conduct at all. Putting a positive gate voltage on, the device starts to conduct. The contacts come back. We start to get the contacts back, and the device starts to behave in a reasonable way that we can change the carrier density from the gate. If we look in detail, we see conductance fluctuation here. This is completely reproducible. This is from both sides of the device. So from measuring contacts on the left-hand side and the right-hand side, it's usually a good indicator that it's not noise, but actual fluctuation in the signal when they agree. I can also plot conductivity here, which is just 1 over resistivity. Resistivity comes down. We start to lose contact. So the reason we get this signal here is we start to lose contacts. But actually, this has been quite useful because the device is already in that variable hopping regime where you want it in the dark at 0 gate voltage. But we're dominated by noise fluctuations in this system. What happens when we put a magnetic field on? So this is that same image again. I've used that image, I think, 3 times now. You can see breaks here. You can see freestanding. If we get the device into that variable hopping regime, got very, very high resistivity here, 60,000 ohms per square. We've completely suppressed any Shubnikov-Haas effect. It's a completely different system to that. Mobility of a few 100 to 200 centimeters squared per volt second. So we've started with a reasonable mobility of about 20,000, and we've been able to reduce that so the device properly sees that disorder. But we're totally dominated here by conductance fluctuations, which is reproducible. These are both sides of the sample. There's a slight change in characteristic here as we change the sweep rate of the field, but irrespective of the field range that we've used, if we calculate this change in conductivity, so conductance variation, it doesn't depend on the region of field that we choose for this conductance fluctuation. What I've done is I've plotted the conductance fluctuation here for both sides of the sample. They completely agree. And we can calculate this in terms of E squared upon H. It's quite small here. It's quite small here. Question is, what's causing that? There's a lot of, this next slide here, there's a lot of data here. I've plotted the root mean square conductance fluctuation as a function of resistivity of the device. This is at constant temperature. What we'd normally do is do a temperature dependence to this. But what I've done is I've plotted out this data as a function of resistance. Now it's slightly unphysical because the resistivity of the device really depends on the size of the device and the scattering mechanisms and so on. The root mean square conductance fluctuation does not depend on the scattering mechanism at all. It depends on temperature, but it shouldn't depend on the resistivity. However, there's several reasons. We're not at zero temperature. If we were at zero temperature, the situation might be different here. We're at finite temperature, and there is a relationship between the root mean square conductance fluctuation and the resistivity. Now it forms, this is data over about 3 orders of magnitude. It's a power law to the -1, which is just the conductivity. So the root mean square conductance fluctuation just depends on the conductivity. There's 2 regions here. There's this Mott variable range hopping region and the diffusive region, diffusive metallic. So KFLM is the product of the Fermi wave vector and the mean free path. That's about 1 between the 2 regions. The device doesn't really see that. Now, to see these conductance fluctuations, the phase coherence length has to be larger than the mean free path, which is interesting. If I replot that data in the metallic regime, so I've plotted this now on a linear scale, I wanted to extrapolate to 0 resistance, to infinite conductance to 0 resistance. What do we get at 0 resistance? Now, I haven't put any fits on here because I don't believe there's a theory that relates resistivity to root mean square conductance fluctuation. But with a bit of imagination, you can imagine they're coming towards 1 over root 2 E squared upon H. And that's exactly what was predicted by Patrick Lee back in the 80s for this behavior, that the root mean square conductance is approximately E squared upon H. The prefactor there, alpha, is about 1, but for a 1D system, it's 1 over root 2. It's not the fact that you're measuring a root mean square value of a quantity, hence the quantity is root 2 times the value. It's because the system is behaving as 1D. And I think what's happening here is that the phase coherence length is becoming wider than the width of the device. Okay, what else can we say about the InGaAs? I'm plotting conductance. This is putting the device in a fridge. These were the ungated devices. This was what the device looks like here, this kind of, this nicely freestanding structure. This is a higher carrier density. This is a function of carrier density at slightly higher carrier densities. These are the freestanding structures. So not really too much happening. Slightly disappointing that the excuse me. The conductance is not thermally activated close to, we're slightly above where the Mott minimum metallic conductivity is. So they are metallic, they're not going into this variable range hopping region yet. And that's because we've illuminated. So we've got a 0 conductance in the dark, but it's because we've got no carriers in the system. The critical carrier density is about 8 times 10 to the 10 when you illuminate in this system. Okay, so a quick summary of the recent data, these thermally isolated, disordered InGaAs devices. Can we get them in a state in which to study many body localization? That's a question. They are dominated by reproducible conductance fluctuations. Yeah, okay. We've got lower carrier densities, we understand that. We have to put a lot more doping into these systems because we have this free surface. and the freestanding devices tend to deplete. If they collapse down, they tend to deplete. We've got partial thermal isolation. There's a large, I forgot to mention that, if I go back, we see a large difference. This is the thermally isolated device. This is the non-thermally isolated. I forgot to make that clear in this. So we've got a large difference in how the root mean square conductance fluctuation behaves between the freestanding and the non-freestanding. Conductance is about E squared upon H, but it's not thermally activated. We're still in that weak, although we put all that disorder in, it's still weak disorder at low temperatures. What I'd like to do is to get these devices more into the hopping regime with the gate. We've got further measurements planned. Question is, if we take out the phonons, what drives the interaction? Is it the Nyquist noise? I think the answer is probably yes. That will drive the interaction. Lots of further measurements are needed, and we've got most of the processing issues covered now, I think. I've taken this, nearly finished now, I've taken this table from a review by Nankishore and Hughes. It's comparing different systems, some of their more interesting properties of slightly different systems. So thermal phase, that's a usual diffusive doped semiconductor. Single particle localized, that's more like the Anderson or Mott localized system. And then this is a many body localized system. So we're comparing some of the properties here. If we're in the normal phase, the system comes to thermal equilibrium. If we're in the localized phase, the eigenstate thermalization hypothesis is false. System doesn't come to equilibrium. True in both cases. Discrete local spectrum for single particle localized, same for many body localized. The overlap between the single particle localized and the many body localized is actually quite large. And it looks like probably the best candidate type of measurement to do is, do we have zero conductance at finite temperatures? That's probably our best way of studying, getting into this system. What next? This is the final view graph, really. What next? What I plan to do is to start to study the wave function phase. This is based on work that was from the mid-80s. Yuri Sharvin's group in Russia saw that if you were in the hopping regime, they had a very, very disordered system that had, it was a lead telluride semiconductor system that had huge impedance, giga-ohm impedance. Yet the electrons showed phase coherent phenomena. They made a series of what we would call Aronov-Bohm rings, an array of Aronov-Bohm rings, and we usually associate that with high mobilities. But he managed to see interaction effects. So phase coherent Aronov-Bohm effects in the hopping regime. These are references to the work here. So that's what will come next when we've looked at the variable range hopping prefactors. And I'd just like to thank Professor Pepper, who's given me loads of slides on this work and that I've included here. So I'd like to stop there and say thank you for listening and taking part in this.
Okay, thanks a lot, Stuart. This was super interesting. I'm going to again tell everyone who's attending that if you'd like to ask Stuart Holmes a question, you can just press the Q&A button if you're hovering over your screen, and you can just say, hey, I want to ask a question, and then I'll give the microphone to you. And meanwhile, people might be writing in there. I had kind of a broad and general question to you, Stuart, which is, so you mentioned that these systems could be good in quantum information processing tasks because of the suppression of the coherence. Is there any kind of large scale project at the moment looking at utilizing them, or is this, what's the kind of ambition with that?
Yeah, so thank you for that question. Yes, I mean, so the large scale is our program grant really to look at that. The problem is at the moment we need to really get more into the problem before we can look at, say, the so-called engineering aspects of it. We need to know a little bit more about the basic physics and the type of measurements to do to really demonstrate that you have a many body localized state. And also issues like, quantum measurement. Do we destroy the state? In trying to measure the state, do we destroy it? Do we fundamentally destroy it? Or does it go through a series of, say, disentanglement? Does it go through a series of disentanglements in the measuring process? So there's lots of interesting questions like that. I think in terms of a practical device, we're years away from a practical device that might be useful. But I think in terms of quantum measurement, I think it's going to be an integral part of our project.
Okay.
Sorry, that was slightly waffly, I'm afraid, but
no, that's okay.
Yeah.
I mean, I guess this is the state of almost all of the quantum information processing field at the moment. So, but is the idea then to use them for like quantum sensing or like potentially as qubits, or do you need to have a better idea of the systems themselves before?
Yeah, I think at the moment we're talking more in generic terms. Yes, we need to know more about the systems.
Right.
Yeah.
So I think
I have a question.
Oh,
so Stuart, how do you know? I mean, have you got some way to quantify the suppression of phonons in these systems?
Well, yes. So that aspect of this work is being carried on by Royal Holloway. So they're looking at thermal power measurements. They are looking at phonon drag type measurements. What we've done here is the pre-study that Chong, Chen and I did was to compare the breakdown of the quantum Hall effect in a suspended and a non-suspended device. Now, you might just turn around and say, breakdown of quantum Hall effect is all in the contacts. Fine. It all happens at the contacts, which are thermally, which are the same in suspended and non-suspended. But we see a big difference in the breakdown of the non-dissipated states with a heating current, so kind of a self-heating. So the device self-heats when it's suspended much more efficiently than a thermally anchored device.
Okay.
But also, yeah, so that's that. But I think also there's some aspects of what I presented today that I just don't understand yet. This conductance fluctuation seems to be very, very different in the suspended and the non-suspended devices. So that's something that I'm starting to look at and try and understand that.
Well, I mean, transport itself is going to be different because you have to have dissipation to see conductance of any sort in a quantum system. So it just means that the dissipation is somewhere else. If there are no phonons in the system or phonons are suppressed, then the dissipation is happening somewhere else. Yes. I mean, I did wonder whether you thought that these conductance fluctuations were basically, coherent multiple scattering UCFs, or whether you thought that maybe the low value of delta sigma came from some other processes going on at the same time?
Yes. So the conductance fluctuation data, I mean, you would think if you've got a high resistance device, it's lost in the resistance. Your small fluctuations are just simply lost in the resistance. But that's generally speaking not true. At finite temperatures, they're not lost in the resistance. They extrapolate at higher temperatures. They extrapolate at lower resistances to the quantity that you're looking for, E squared over H. Why that should be, I'm not sure, because the actual resistivity is dependent on interaction. Whereas if you read the papers by Patrick Lee, interaction doesn't come into it. You calculate the conductance fluctuation, interaction doesn't come into it. So I hadn't appreciated that. I don't know if I've missed. Is that well known now?
Yeah. That's a very good question, Stuart. We'll wait for your next seminar.
I'm hoping that the conductance fluctuation will get us into understanding the freestanding, the disorder in the freestanding structures.
So I think we have a question first from Thierry and then from Ulrich.
Hi, Stuart. Nice to see you.
Nice to see you also. Thank you.
Actually, a very quick question like that, and then maybe another question, if it's okay with you, David. Did you see any re-entrant MIT at low temperature? Because this is something which I've been studied and sometimes seen in those systems. So I was just wondering if you saw that.
We haven't got enough data on that yet. I think the Arindam Ghosh work, were you involved in that Arindam Ghosh work?
I was not on the paper, but I remember what he.
So is that the work that you're referring to? Some of the work that you're referring to, that you start to see a re-entrant behaviour.
Yeah.
Yes. I mean, I've only picked up what I've read in his papers, basically what's in the literature. So we haven't seen that yet. We don't have those detailed measurements yet.
Right. Okay.
But I think if you're looking in the literature, people are slightly selective with their range of data.
Yes.
I think people are selective with their range of data. Yeah.
I mean, the other thing about the suspenders and structure, I mean, I had the chance to work on a few of them in the past, but it's on silicon, not gallium.
Yeah, silicon, yeah.
Not
yeah.
3.5.
Yeah.
And I remember that to get an idea on the phonon spectrum is quite it's quite a thing.
Yes.
It's quite difficult to get an idea. So I was wondering if there was the possibility to change the shape of your suspended structure, because I know it's very very dependent on the shape of it.
Yeah.
And there are many parameters, and so maybe varying those parameters can give you some insight. So that's what I recall from the few experiments I've done on it.
Yes. I think it's easier to make suspended devices in silicon, I think, just from a purely practical point of view. So
yeah, you don't want to overetch it too much.
Things disappear when you overetch them.
Yes.
So, I think you'd be able to study that in silicon. I think in the 3.5s you'd be lucky to study that effect. We'll be after 8 months of making devices in the clean room. I think you'd be lucky to study that in the 3.5s. You have some control over the freestanding thickness, but the actual shape, I'm not sure.
Well, I mean, if you have the thickness and the width, for example, it's already two good parameters.
Yeah.
The length is another one, but as far as I remember, the two critical dimensions were those. Yeah.
Yeah.
All right. Okay.
Sorry.
Thanks.
So I think Ulrich had a question.
Yeah, thank you very much. And thank you very much, Stuart, for this wise talk.
Thank you.
Glad to see what you can now do. I, of course, come from a very different community in Conductance, where we look at MBL in a different context.
Yeah.
But there have been quite a few papers in that context where people said that you can use them in quantum information really as almost perfect qubits.
Yes.
Because they are not ergodic, because they only have a very weak coupling to the environment. And there have been like some proposals by Eugene Demler and others, where they can say you can do something like Deer responses. So if you want like a many body spin flip process, and then the wave function recoheres, and you get like your original quantum information back in a very small area after quite some long times.
Yeah.
So I don't know how much. This is very hard to do in Coulomb, but I'm wondering whether this kind of like generalized spin echo responses are possible in your systems.
Yeah, I think that's an interesting comment. I think that would the reason for looking at the InGaAs was the kind of the unique spin properties. So the idea there would be to use an electric field to probe the spin property. I think we'd struggle for more sophisticated spin echo type measurements, which I assume are at hundreds of megahertz, perhaps. Not without problems. I mean, we could start to study that. trying to study more the DC properties.
Okay.
Was there more to your question? I think you mainly made a comment.
The thing I wanted to just, my question was whether one can do these spin-echo things in these systems.
I'm not. I don't know why. I don't know if there's a reason why not. I should actually say. I'm sorry, it's not quite my field. I know roughly what you're getting at.
Okay, fair enough. Thank you.
I can't add to that.
Okay, so do we have any more questions? I think the list of questions has now been finished. If anyone has a final question for Stuart Holmes, please just post it. But I think with that, I think we're probably done with today's seminar. Thank you very much for giving this super interesting talk. It will be extremely interesting to follow what's happening in your lab over the next few years. And yeah, thanks to everyone for coming. As usual, the kind of Cavendish QI group will now have its group meeting. So kindly going to ask everyone else who's attending to press leave meeting, and then I'll see you all next week.